Okay, off we go. So here's where we were last time. We were talking about various different examples of how to compute vector line integrals and vector surface integrals. And remember, we have a whole bunch of tools for this purpose. And one of the big questions is, how do I know which tool to use? Right? So you can be an expert at using the fundamental theorem of line integrals, but if you don't know to use the fundamental theorem of line integrals, what does it do for you? Okay, so that's really underneath it all my main incentive for these various examples. We've already talked about all of those techniques themselves. So I'm going to focus on the diagnosis, and I'm not going to get very far anyway into the nitty-gritty details. Okay, so reminder, what we were doing last time with this example, we had identified that we are in three-dimensional space. We're computing a vector line integral. We've thus identified on our diagram that that is our context, right? We're in 3 dimensions looking for a vector line integral. Okay, so right off the bat, and I think I made this comment last time, you immediately know that there is no way that divergence is going to have anything to do with this computation, right? So my advice, again, keep in mind, the goal is not to get the answer at the bottom of the page. The goal is to impress the grader with your understanding of the ideas, right? And pursuing things that have no chance, well, you know, in a subjective assessment of trying to figure out how much this student understands, not a good look, is I think how I said it last time. Okay, so likewise, there should be no triple integrals. There should be no discussion of Gauss's divergence theorem. None of that has any relevance, possible relevance to the question. Okay, so the diagram points that out for us. The diagram also suggests we should take our integrand and compute the curl, and we should take our domain curve and look at the endpoints. And I think we did part of this last time anyway. We wrote down the curl. The diagram will keep you straight when you whoopsie, right? The curl of this vector field, and y'all can check me later on the computation. I think it works out like this. It's not 0. Back to the diagram. Let's see, let me get rid of the mess here. It is not 0, so there is no antigradient. So the fundamental theorem not gonna apply. Don't try. Don't waste your time looking for an antigradient. There is none. Don't write down the fundamental theorem of line integrals. It has no chance of working. Right? Okay, so fine. Let's consider the next thing. We're going to think about this curve and does it have boundary points? And in this case, a case could be made that maybe this is an unnecessary little exercise, but this cylinder intersected with this plane. Let's see, the intersection curve then is going to be an ellipse, and you will notice it doesn't have any starting or ending points. Right? The diagram tells us then that because there is no boundary, then there must be an anti-boundary. This curve is the boundary of some surface. By the way, my little favorite little pithy phrasing of this is that every curve either has a boundary or is a boundary. Rolls off the tongue very nicely, right? So that's another way to think about it. Now in this case, of course, we can look at our picture, and the picture makes it actually pretty clear from the get-go. Oh, whoopsie, that's the wrong tool. Pretty clear from the get-go that, that curve is kind of obviously a boundary. In fact, there's an obvious surface whose boundary is that curve. Okay. All right. We also have to think about orientation. Okay, so we'll deal with orientations if we find that we need to get to that. Okay. So what I see, though, going back to the diagram, because let's see here. Let me clean up the mess. Because we've established that there is an anti-boundary surface, Stokes' theorem is on the table. And conveniently, we've already computed the curl Right? We've already gotten some use out of having computed the curl. We've concluded that the fundamental theorem of line integrals won't work. We've saved ourselves loads of pointless effort there. And it's also going to play in by being the integrand of our new flux integral that we're going to get by way of Stokes' theorem. Is everybody on board? Everybody following? Notice how the diagram just keeps us organized, keeps us on the right track. Right? I think it's really, really helpful for this. Okay, so I think this is about where we left off last time, and so we can rewrite this integral, color choices, this integral that we're interested in, by Stokes' theorem is a flux through this surface S of the curl of F dot little n ds, or if you want to say ds scale, ds vector, also fine, right? So, okay, but I'm going to write it like this because I'm going to hope to take advantage of some geometric convenience. After all, I can easily see what that normal vector is there. That just reads straight out of the equation of the plane. And then you notice that our surface that we're interested in is part of that same plane. And so has the same normal vector. And yeah, I got to worry about orientations and something to think about. But other than a plus or minus, I can read the normal vector straight off of the given in the question. And so this normal vector is just, 1, 1, 1. And of course I have to make it a unit vector. So there you go. Right, so there is a surface integral now. And by the way, arguably really good news, right, is the easy dot product to write down. Let's see, so I can rewrite this integral as surface integral of, let's see, minus square root of 3. Oh, plus or minus, sorry, careless, sloppy me, plus or minus, not sure yet. Got to worry about possible orientation issues. We'll think about that again if the issue arises. And, ds. And it's tempting to say, well, this has worked fabulously. Right? I mean, we turned a vector line integral into a new kind of an integral. The integrand was a constant. That's nice. The dot product ends up being a constant. It's a dot product, it's a constant that's over a somewhat recognizable geometric figure, right? It's a solid ellipse, in some angled plane. It's just an ellipse, right? And here's the sticky wicket on this one. How am I going to compute the area of that ellipse? Oh gosh, if I was going to use regular old high school geometry on this, I'd have to know the major axis and the minor axis. How am I going to know where those are? And it's not that it can't be done, but frankly, it's needs a little bit of legwork in getting that to work out. And this actually ends up being not that convenient. Even though we got it down to the seemingly very nice answer of known constant times area, there's actually a lot to be done in figuring out what that is. So I'm going to call this one a disappointment. Right? In fact, now keep in mind, this toolbox full of tools, they are tools, not wands. Right? So this is not anytime one of these theorems apply, you just wave the wand and boom, answer comes out and it'll always be convenient, it'll always be awesome. It's just not the case. Wouldn't that be nice? But it's just not the case. And this is one of the cases where, frankly, I don't think this has been helpful. Right? I think the best way to solve this problem is to parameterize this curve and pull back through the parameterization. And it's just not that hard, frankly. I mean, the vector field's not that bad. The curve, it's not that bad. You'll notice, for example, from this part, you can conclude that x and y are doing something like cosine t, sine t, and then you can take these and plug into there and conclude from the equation of the plane that means that z must be, whatever that works out to be. And boom, you got a parameterization. I think that's probably the easiest way to do this problem. Right? So again, my purpose here with this example is to make sure that we're clear that while these tools are very, very useful, they don't always give you the best possible solution. So keep an open mind, right? Identify all your options. Sure. Absolutely. And then think kind of critically about, wait a minute, which one of these is actually going to be the best solution? And it's not always the one that uses the big gun. Okay. Pausing. Questions? Everybody on board? Okay, moving along. A very similar looking question. Again with the, same vector field we saw previously. Again with a curve that again is a plane intersected with that same cylinder. The only difference now being that this is a different plane. Alright. And again, we're computing this line integral. So a lot of this example goes down really, really quickly. We already know it's the same vector field. It's got the same curl. It's still not zero. There's still no anti-gradient. We still can't use the fundamental theorem of line integrals. This is still a boundary curve. Stokes' theorem still on the table. A lot of that diagnosis is just the exact same that we did here. Right? So this was out. This is in. And we've got an anti-boundary surface, and so we're going to use Stokes' curl theorem. Now again, no promise this is going to work out great, but let's give it a try. So let's see here. We cite Stokes' theorem. We'll have flux through our surface of the curl, still the same curl, dot NDS. Kind of looks like we're heading down that same road to bad news, right? But always good to think it through. If you look at this same cylinder, and you look at this same, color choice. Okay, fine. This same plane, and again you look at this intersection. Again, it's an ellipse. Again, I can write down the normal vector for the plane, which is also the normal vector for the new surface, which is part of that same plane. Right? Seems like we're doing exactly the same thing. This time, though, it does work out a little bit differently. This time, this normal vector, just a little bit easier. Again, it comes out of the equation of the plane. 1, 0, negative 1. Don't forget to divide by the magnitude. It's got to be a unit vector. And the beautiful thing about this is that dot product is 0, and game over, we win. Right? So little subtleties can make a world of difference, right? So that's the purpose of this example. Sometimes, even though Stokes' theorem might be kind of useless in a certain context, in a very similar context, it might be awesome. Right? So in a case like this, you definitely not want to go down the relatively tedious road of parameterizing the curve and blah, 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 pullbacks. Not that it wouldn't work, right? But it's not the best solution. It's not the best mathematical thinking. This is the way to go on this example. Stokes' theorem kills it here. Right? How are we doing? Is everybody happy? Is everybody... Yeah. Mm-hmm.
So you said it wasn't an anti-gradient when you actually did it.
Right.
But couldn't you just do the method where you just take the integral of each of the coordinates?
And you can go down that road and try to play that game. And I'm sorry to report that game is rigged against you. You will never win. Yeah. No, but it's a good exercise. It's a very good thought, right? So just for funsies, I'm going to encourage you to try it. Right? And because it's useful to see, wait a minute, why can't I make these pieces fit? Right? And you will just find yourself very frustrated, and so that's how that plays out. Yeah. Anybody else? Great question. Everybody's good? Alrighty, let's do the next one. Okay. Yeah, so now still in 3 dimensions here, as you see by 3 components to the vector field. This time we're computing a flux, though, so all of the sort of diagrammatic strategery all changes. So we are now still in R3, but looking at a flux. And that means, don't even write down the fundamental theorem of line integrals, doesn't have a snowball's chance, forget about it, no good, no possibility, bad look. Right? So don't even write that down. Don't try to find an anti-gradient. It's a complete waste of time. It's got nothing to do with the question at hand. Right? Okay, sure, right, fine. Okay, so apparently, according to the diagram, whatever our vector field is, I should compute now the divergence of it. Along these lines, don't compute the curl of it. Again, bad look, right? So, if on your page, in a situation like this, you take the vector field and you compute the divergence of it, that shows some understanding of possible diagnosis of a solution. That shows some reasonable progress. If you compute both divergence and curl, right, then it makes it look like you didn't know which one of those was the one that had the chance of working. You're making yourself not look as good, right? So again, bad look. Avoid the bad looks. Doesn't make any sense to compute that curl. Okay, let's see. So we're going to compute the divergence, and then we're also going to think about our surface, and we're going to think about, wait a second, does that surface have a boundary curve? If it has a boundary curve, then there's no anti-boundary, and that'll affect whether we can use the divergence theorem. Okay. All right. I can compute the divergence by doing 0 algebra. I think this is a good thing to be on the lookout for. I don't even have to, even though the divergence computation would be pretty straightforward, we still don't even have to do it. I immediately know divergence is 0. And so good thing to be on the lookout for. It says right here, our vector field is a curl, right? F is the curl of that thing. Right? Okay, so knowing that it is a curl, back to the diagram, my vector field that I'm interested in is the curl of something. In fact, I even know what that something is. So what's the divergence? Lifetime theorem tells me immediately divergence has to be 0. Is that cool? Everybody happy? Okay, so what does that mean? Well, in fact, case could be made, I didn't even really need to compute the divergence. The whole point of computing the divergence here was to decide whether there is an anti-curl, and it actually tells me right here that yes, F has an anti-curl, and there it is. Right? That's the thing whose curl is F. So we got ourselves an option here where we can definitely apply Stokes's curl theorem if we are so inclined. Right? All I would have to do is take my surface and look at the boundary curve and compute the line integral around that boundary curve of my anti-curl vector field, like so. Okay, so let's see what that would look like. Does that work out nicely? So let's see. Stokes's theorem tells me again right off the bat that I can compute this as a line integral over the curve, specifically the boundary of our surface, of the anti-curl, 0, 0, XYZ. By the way, be very, very careful, please, not of F. Right? This is not, we're not looking at a line integral of F here. Right? We're looking at a line integral of the vector field whose curl is F, because that's what Stokes's curl theorem says. If you get the vector field wrong, again, it's an easy sort of little whoopsie, right? Easy whoopsie doodle, but that's part of what the diagram offers, right? The diagram offers a straightforward, almost effortless, free way to avoid these kinds of mistakes, right? If you've been asked to compute a flux of some vector field. And if you're going to do so by computing a line integral, it says right here that that vector field should be the one whose curl is what you were given. Right? So let the diagram be your guide. Follow the diagram, and it will, again, help you avoid these kinds of mistakes. So there you go. Let's see now, dot in DS. And we better figure out what our curve is. Now let's think about the surface. The surface, there it is. Y'all might even recognize, we just did an example last time that involved the surface. It looks a lot like this one. That surface is an upside down paraboloid, and specifically just the part above the XY plane. It is an open surface, right? Now, when we draw the edge, there's going to be a temptation to imagine that somehow that includes this here. It doesn't. Right, very importantly, right? It doesn't say anything about, and by the way, tack on the part where z equals 0 inside of this parabola. Doesn't say that at all, right? So that is not there. This is an open surface, upside down cereal bowl, and the cereal has all fallen out. Okay, so let's see here. Apparently what we need is, wrong color. We need to look at this surface. And we need to look at the boundary of that surface. The boundary, of course, is that curve. And this is another situation where, you can write down details if you want, but we don't need to. It turns out that kind of at a glance, we can see everything that we need to know about this boundary curve. All I need to know is, okay, sorry. I was moving a little too quickly here. Don't trust me. Keep me honest. All right. I made a boo-boo. My intention was to write down the line integral. Line integral of the anti-curl. This is not how line integrals end. Right. Sorry about that. Again, make sure to keep me honest. Stay on your toes. Line integrals end with dot t d little s. All right. This is our dr vector. Apologies. Everybody, let's take a moment to make sure everybody's comfortable with why it's TDS. Everybody happy with that? But y'all probably, I assume, made the same mistake I did and just were busy thinking. I was busy thinking about other things and how this is going to play out and et cetera. I'm just mindless. So let's call this. Look how easy it is to mess that up. Right? So keep it in mind. Make sure to be careful. Okay, so so the only thing we need to know apparently about this surface, this curve, is I need to know the t. I need to know the unit tangent vector, and in fact, even though that tangent vector to the curve, to write it down exactly might be a little hard. The mere geometry of this situation tells me one thing immediately, and that is that t vector is horizontal. Right? I mean, the entire curve is in the plane z equals 0. We're moving around inside of z equals 0. Z doesn't change. That vector is horizontal. And if it's horizontal, I don't know exactly what it is, but this third coordinate is 0. That makes this dot, it makes this dot product 0. We're integrating 0. The answer is 0. We win. Works out really, really nicely. Yeah?
Is there a reason you don't use surface independence?
No, that's great. That's a great question. And that's going to be my next move. Yeah, totally. Yeah, absolutely. The reason I use Stokes' theorem here is because I can, and it works great, and it's one of two excellent solutions, and yours is the other one. Yeah. Before we move on to surface independence as it applies here, how are we doing with how we use Stokes here? Everybody's all right with that? Okay. One thing to keep in mind, in order to use Stokes' theorem, to compute a flux as a line integral, notice you do need the anti-curl. You may also remember, I have never told you how to compute an anti-curl. This is because it's not easy in general, right? So, in fact, this kind of thing doesn't really happen a whole heck of a lot, that you can use Stokes' theorem kind of, you might say backwards, where we compute a flux with a line integral. Finding anti-curls is in general hard. What made it possible here is that I gave you the anti-curl. I gave you the anti-curl in sort of a coded way, right? And you have to look at that and think about what it means and interpret carefully, at which point, you look at this on the diagram and it's pretty immediate. Oh my gosh, look at that. That's totally the anti-curl, right? But you do have to be thoughtful. I didn't label it as, hey, by the way, here's the anti-curl. Okay, so let's talk about that other solution now. Another perfectly good solution, arguably better, depending on how you choose to think about it. And that is, again, looking at this hint, it says right here our vector field is a curl. Going back to the diagram, the vector field that we're interested in, we're given that it is a curl of something, and it immediately follows, not only does it immediately follow that the divergence is 0, it also immediately follows that it is surface independent per our usual. This is one of the special vector fields in that position in the diagram. Right? So surface independence, also freebie on the table. All you have to do is acknowledge it. Right? So in particular here you could say implies F is surface independent. Boom. Okay, now again, surface independence is a great tool. We've got a lot we can do with it. Let's we do have to think about our surface. Our surface again looks kind of like this. The boundary of the let me label this as S. The boundary of S is going to be something like this. There's boundary of S. When I say surface independent, and when I choose to use a new surface, keep in mind the big asterisk. Pick any surface you want with the understanding that you have to maintain the boundary. Right? A lot of students forget this and say, oh, I don't like that surface right here. I'm going to use this surface over here. And that doesn't work. Right? It doesn't make any sense. It doesn't have the same boundary. Surface independence is good, but it's not that good. Right? Okay, so what's your favorite surface that has that same boundary? My favorite surface that has that same boundary is this one right here. Again, just like the example we did in class. It was either last time or recently anyway. Okay, so there's my new surface, and again, our integral that we've been asked to compute by surface independence. Here, I'll keep my colors straight. By surface independence, I can rewrite that as flux through now my new surface. Oh gosh, what am I going to call this? I'll call it D, I guess. Flux through D. Same vector field. F dot ds. Right? Again, so this is surface independence. By the way, common mistake that I see on exams when students are trying to use surface independence is, and I understand that these ideas, there's a lot going on, right? But sometimes it gets a little jumbled and students feel it necessary not to use F, but to use like the curl of F or something, right? And again, that's not what surface independence is. Surface independence says same vector field, right? It's not a boundary theorem. It's a change the domain, keep everything else the same kind of a theorem. Okay. So again, careful, don't misapply. And now let's think about what we're going to do about this. By the way, I'm going to go ahead and rewrite the ds vector as as little n ds scalar. And now let's start writing stuff down. What do we know about this stuff? Let's see, our vector field is xz minus yz 0. And our normal vector, well, again, there's orientation questions, and we'll cross that bridge when we get to it, but plus or minus, that's our normal vector. It's either straight up or straight down. And so our normal vector here is 0, 0, plus or minus 1, not sure. And again, it kind of turns out that it doesn't matter in this computation because whether it's positive 0 or a negative 0, the answer is still 0, right? So dot product is immediately 0, and so we're done. So another lovely solution. All right, take your pick. I'm not clear in my mind which of these awesome solutions is more awesome, but they're all, both of them are super. What do you think? Everybody on board? All right. Okay, last example. Again, 3 dimensions. Again, computing a flux. Again, I need to identify our context on our diagram. We are in R3 looking at a flux. Again, the diagram tells us compute the divergence. Who knows, might be useful some way or another. Look at your surface and think about its boundary curve. Might be useful one way or the other. And then let's take it from there. Okay, so the divergence of this vector field is, let's see here, 1, which is not 0. Okay, so immediate conclusion. Not 0 means there is no anti-curl. That means Stokes' theorem is off the table. Again, don't try, bad look, all that business. Okay. How we doing? Okay. Okie dokie. Next, I want to think about the surface. Now again, you can look at the boundary curve toward the question of deciding if there is an anti-boundary region, as I like to call it. And, sometimes it's useful to think about the boundary toward that question, but sometimes it's really not necessary. And in this case, it says right here, unit sphere, right? So, I know what that looks like, and orientation issues we'll entertain for a moment, but modulo possible orientations, that's clearly a boundary of a solid. It's that solid ball on the inside. Right? Everybody good? Okay. So back to the diagram. We have this surface in R3, and it is indeed a boundary of some region. By the way, I have already computed the divergence, and I got 1. Right? And so not only is Gauss's divergence theorem on the table, but I have everything that I need to use Gauss's divergence theorem. I've got my integrand is the divergence. It's 1. And I've got my new domain, which is the anti-boundary solid, namely the thing whose boundary is the sphere, namely the ball. Is that cool? Everybody with me? Okay. All right. So, again, thank you, diagram. We better think about orientation on this one. It does say oriented inward. The answer is not going to end up being 0, so it's not going to just kind of disappear into irrelevance. Oriented inward means it's not technically a boundary as written. Okay, fine. So we're going to orient. We're going to think about this surface that is oriented outward, and I'm going to say what we've been asked. The flux through the inward oriented surface that we've been asked is the negative, because of this orientation issue, the negative of the flux through the boundary of the ball. f.ds. And now we've got a boundary. We've dealt with the orientation. And because it's a boundary, we can immediately write down the divergence theorem. Minus sign comes along for the ride, of course. Triple integral over the ball of the divergence dv. We've already computed the divergence. And we just have an integral of 1 over the garden variety unit ball, easy volume. Boom. Don't forget about the minus sign with orientation. And we're done. How we doing? Everybody happy? Yes.
So in the case that divergence was 0, then we just wouldn't be able to use Gauss's divergence theorem to evaluate?
No, actually, I hear you. But no, if the divergence is 0, that means that you could consider using Stokes' theorem.
Okay.
Right. It doesn't mean that you can't use, yeah, right. So 0 is pure good news, not bad news. Does that make sense?
Yeah.
So if the divergence had been 0, I mean the surface is still a boundary modulo orientation issues, and we still use the divergence theorem. It's just that now our integrand is 0, and it just makes the arithmetic easier. Yeah, so it's all fun.
So the overall solution would just be 0.
Yep. Yep. If the divergence had turned out to be 0, then the answer would be 0. Critically, because we can use divergence theorem, and the reason we can use the divergence theorem is because our surface is a boundary, right? So what you don't want to make the mistake of falling for is this idea that if the divergence is 0, then your integral is obviously immediately 0. Nonsense. And by the way, I have another supplemental video that I recorded a couple of years ago addressing exactly that point and some analogous points related to the other accumulation theorem. So I'm going to post that up on the YouTube channel sometime pretty soon and give those a watch. But yeah, so you can only cite the divergence theorem if your surface is a boundary, and otherwise you can't cite it at all. It doesn't apply. There is no triple integral to even talk about. Right? So something to be very careful about. Okay, all right. So that's our examples. We're done with chapter 7 now, and back to chapter 4. Y'all will recall we skipped chapter 4. Well, it's not the right word. I didn't choose to do it in numerical order because there's so much stuff in chapter 6 and 7. Excuse me. So much stuff in chapter 6 and 7 that you need as much time as possible to digest, right? And now you know what I'm talking about. There's a lot of stuff there, a lot of stuff to give time to sort of sink in. This chapter 4 stuff is largely algorithmic. It's largely, not entirely, largely analogous to stuff we already saw in single variable calculus. And so I expect this is going to go down pretty easy. It is always something that we do pretty quickly in this course. So here we go. 4.1 is super quick. I'm going to start by reminding you of this thing called the Taylor polynomial. Right, this thing right here. And y'all have seen that before back in Calc 1 class or Calc 2. No, Calc 2. I guess Calc 2 class. Right? Why do we care about Taylor polynomials? What are they good for? Pretty good question, right? It's nice to have a crisp answer on hand for why do we care about Taylor polynomials. And my favorite answer is it is the unique polynomial of the appropriate degree that mimics the function in value, derivative, etc., and higher derivatives all the way up to whatever degree of polynomial you want to talk about. Right? It's the best, simplest approximation of the function. So really nice. Make sure you remember all of that stuff. Of course, by the way, make sure you're good with computing Taylor polynomials. So likewise for multivariable, it's actually pretty similar. similar story. What we're going to be looking for when we define the Taylor polynomial of degree k. I just want to know what's the polynomial of the appropriate degree that best approximates the function, that's the best mimic, that, rip off of the given function f in terms of value and derivative, et cetera, et cetera. So, best approximation in terms of value, derivatives, partial derivatives, of course, various higher order partials, and all of that. Same idea. And good news, we can write it down. Now, our textbook does write down the general formula for the, degree k, arbitrary degree k, Taylor polynomial of a multivariable function, and it's pretty weird. It's not super easy to write down. It's a notational, awkward. Okay, so we're not going to deal with the full Taylor polynomial. I'm just going to talk about the second order Taylor polynomial. That's it. Right? And that actually is not that bad to write down. Here it is. Gosh, it looks kind of similar. Value of the function, derivative times displacement. I mean, it's just, in first order, it's really, really analogous. And the interesting part is the second order term that you may recognize is a quadratic form. And flashbacks to linear algebra class, right? So quadratic forms, they come up in various different ways, and this is one of the big ones, I think. Okay. So now, what's the matrix that defines this quadratic form? It's this thing right here called the Hessian matrix. And notice, it's a very organized little array of expressions. It's just the elements are these the various second partials of your function. Right? Mixed and unmixed, right? But organized in the obvious way, right? That's all it is. It's the matrix of second partials. So you put that into that spot, and you all know how to compute quadratic forms. And boom, there's your second order Taylor polynomial for whatever function. Okay, that's section 4.1. There's other stuff in section 4.1, again, that, make sure to read it. A lot of that should look familiar, I hope, and is pretty readable. So, moving along. 4.2. A quick reminder of how single variable optimization works, and I think this will look familiar. Y'all probably remember, let me just cut to the punchline, the definition of a critical point. I just want to make sure we're clear on where that comes from. Why do we call these critical points? And the answer is, these are points that we can't eliminate as possible maxes. Now, what do you mean can't eliminate? What's this eliminate business? The actual active mathematical reasoning that we do when we do optimization is an elimination process. There's a list of conditions that I can write down for a point in an interval. By the way, let's consider this interval right here from A to B. There is a list of conditions I can write down, and let's think about that point right there, for example. If a point in our domain is comfortably in the interior, it's not an endpoint. If the function is differentiable there, and if the derivative is not 0, definitely not a maximum. Right? There's no way that could be a maximum. How could that possibly be a maximum? The function's still getting bigger. No way that could be a maximum. Right? And this applies to the great majority of points in the domain. So for example, this one right here, now it's tempting to say, hey, wait a minute, the function's getting smaller as I move to the right. Yeah, fine, but it's getting bigger as I move to the left. So even though the derivative's negative there, yeah, sure, okay, fine, whatever. Non-zero means that one way or the other, the function's still getting bigger. Right? So this is our main tool in optimization, is to eliminate points. And the cool thing about it is this allows us to eliminate the great majority of points in this domain. The only points that we can't eliminate, let's see here if I can fit this on, are points that are boundary points. I might need to go in a direction that I can't go because I'm on the edge already, so that might be a problem. Points where there's a differentiability issue, derivatives don't really tell me anything if there is no derivative. And then points where the derivative is 0. Points like that. Derivative is 0, I can't just make this claim of, well, it's obviously increasing. Because it isn't. Right? The derivative is 0. So, we call these critical points not because we know what's happening there. We call them critical points because we don't know what's happening there. We know what's happening everywhere else, except for those points. Those are the ones where we're like, I have no idea what's going on. So we call them critical points, and then check the values and see where the function's the biggest. Right? That's our general process. Okay, it's the same in multivariable. Shockingly similar. We have an argument that eliminates most of the points in the interior. Most of the points in the interior, and by the way, to be clear, here we're looking at a function of two variables on a domain like this. And so z is a function of x and y. There's our domain. I can eliminate most of the points in that domain by just saying, well, this point right here. Oh, whoopsie. I wanted to be in pencil mode. This point right here is in the interior. Whichever direction I might want to move, I can move in whatever direction because I'm in the interior. And the function's differentiable, and if the gradient is non-zero, the gradient will point in the direction in which the function is increasing. And therefore, again, there's no way that could be the maximizer. The function's still getting bigger. So we eliminate the great majority of points in the domain, missing then only what we call critical points. Critical points being points that are either on the boundary. Now I can't just move in whatever direction I might need to move to make my case. Obviously, if there's a differentiability problem, I can't cite the derivative as telling me something. And if the gradient is 0, then the function isn't changing at all as I move, and so I can't claim it's getting bigger. So, kinds of points that we can just, we can eliminate everything except for these points, such as, again, differentiability problems, flat points on the graph where the gradient is 0, such as that and that, and boundary points. And by the way, let's take a quick moment to recognize that boundary is a little scary because when we get to the point where someone says, okay, you've got a handful of critical points, why don't you just check them? Well, I've got 4 interior critical points, but I have infinitely many boundary points. I can't just check them. I don't have that kind of time. Right? It's not feasible. So we're going to need a sophisticated tool for dealing with the boundary, and we will definitely have that tool. Anyway, real quick, that's going to be our big strategy. And let's see, how am I doing on time? Well, you know what? Let's draw the line right here. Call it a day, and we'll pick up from here next time, ending a little early. See y'all later. Have a good weekend. Don't forget we have a test coming up on Wednesday, I believe it is. See ya.